Dear participants, today it's a wonderful day, and we are going to listen a talk on a very important topic, which is computing paradigms in next generation networks. Mr. Sudhir from Cisco will be talking about edge computing, fog computing, mist computing, cloud computing, and in fact he will be also explaining what a cloud is, why a remote server is not called a cloud, right? So all the nuances of the cloud or computing technologies which are now prevalent everywhere, and almost all of us are users of such platforms. So Sudhir will be explaining this very well. So let's stay tuned and be excited about the details, right? So regarding Sudhir Kayam Kulangara, have I pronounced it correctly? Kayam Kulangara.
Absolutely, yes. Correct.
Yeah. Correct. Sudhir has almost about 24 plus years of experience in telecommunication engineering, working with Tier 1 premier most equipment vendors and semiconductor companies. Prior to his current role, he has also worked with Intel Corporation, where he has developed technologies for LTE networks. His past experience includes the architecture of several carrier class switching and routing solutions in Motorola and Alcatel-Lucent. His current area of interest includes edge computing, segment routing, XOL network, and network modernization. So he holds multiple patents in the area of related to radio access networking technology. So let us welcome Mr. Sudhir Kayam Kulangara for a wonderful talk on various nuances of computing. Yeah, welcome Sudhir. Please go ahead.
Thank you so much, Professor Rajput, for the nice introduction. It's an honor to come and give a tech talk to one of my dream universities from childhood, where I wanted to study my engineering. I ended up studying somewhere else, but it's still my dream. Okay.
Now you are tuning the students who are studying there. So this is another great honor. Yes.
It's an honor for me to talk because it's like I said, it's one of the most respected universities in India and abroad, because I know the ITBHU stars, the original BHU stars. Yes. I work with, they're very, very well respected in the industry. Yeah. So talking to a crowd like that, it's an honor. So without much delay, let me give a brief overview on what I wanted to focus on. Right. So I come from a networking background, and I'm actually a person going through a transformation. I personally go through a transformation to follow the industry transformation. That's what I'm going through. So if you have looked at the history, when I started working, it was all about telecommunication network. That is all the class 5, class 4 voice switches and all of that. Then people started running the data, 64 kbps kind of data over the satellite links or the simple T1 links. The bandwidth consumption was very low those days, right? I'm talking about mid-90s when I started my career. Then, from there we slowly moved through a transformation. That was during the beginning or early stage of my career. I have seen the telecom network getting transformed to accommodate the datacom. Right? So a merger of the telecom and the datacom networks happened towards mid to late 90s. That was one of the major transformation that telcos have gone through, in my lifetime that I've seen. And we are at another tipping point where we are going to go through another major re-architecture. This is not an upgrade. This is a major re-architecture of the entire application infrastructure. So from the telecom infrastructure to the datacom infrastructure to what I'm going to call it application infrastructure. And that infrastructure includes, the entire data network, your compute infrastructure, and all other layers that you need to enable the next generation applications, right? So I'm not just going to focus on the cloud or the edge today. I'm going to run through a story to explain why we need the edge computing, or why are we going for this major transformation. Definitely, I will talk a little bit about how and what kind of things, but why is something that we need to get answered to before we talk to the rest, right? So if we need to have another conversation to talk about, details of the cloud, we can definitely have it. But just let me take a stab at why part today. So I'll just skip through this. So let's look at application landscape a little bit. June 29, 2007. One of the important dates in my, in the overall technology industry. If you ask me about this day, I would say this day in general divided the application scenarios into two different eras. The era before this and after this. Those who have used mobile phones or computers before this date, the user experience was very, very different. When Apple introduced the iPhone and allowed us to install the apps through their iTunes software in the first release, that changed the entire perspective of the applications. Later on, they introduced the App Store and a bunch of other things, We saw cool applications like WhatsApp coming and taking over some of the traditional telecommunication services. But if you ask me, this is the single date that changed the mindset of the end user, right? So without talking about it, I cannot move. And from there, we have moved along a lot. And, we are at a stage, some of these dreams are coming to reality, right? One of the major things that happened during the pandemic was many people were forced to stay back at work, and it impacted the productivity and the manufacturing industry a lot, because manufacturing is one industry that rely on people to come to the assembly floor and take care of step-by-step processing in the assembly line. And when they're forced to stay at work, it impacts the production. And some of the industries have done the transformation before the pandemic, but rest of them who has not done it, they all are talking about complete industrial automation of the industries. I'm talking about the Industry 4.0 kind of applications, right? That's bringing in a big change. So think about it, what is happening. In a typical factory floor, you have hundreds of people working on the assembly lane. They make sure that, a product from its early stage, which is a supply, all the raw materials, it go through different processes, and there is a human intervention at many places. And it requires a lot more coordination. Now we are talking about replacing them with robots, which essentially mean that you need to have a whole lot of sensors to collect the data from each one of these, mechanical entities, send it to a computing location, process it, take the outcome of that process, and push it to the next chain in the assembly line. Requires a lot of bandwidth because you're pushing data from a lot of sensors, and needs huge compute power. Again, you're dealing with a lot of numbers, and getting the right information from that huge pool of data, it's going to take good amount of compute power. And third, you have to do this in a very, very deterministic fashion. I'm talking about low latency there. So I just picked Industry 4.0 as an example because it's easy to understand. But if you switch back to look at a Tesla car, which they call, there are like level 3 kind of Tesla cars available in the market, which is trialed in some of the North American locations and Europe, right? So what in a nutshell, if you look at these cars, it's like a cluster of sensors. You have few hundred sensors attached to a car with a lot of radar sensors, lidars, then simple signals, video cameras, all of them capturing gigabytes of data every minute and upstreaming it to either a edge computing location or a co-located compute where all of this get processed. Like our brain process the data. Think of when we are driving the car, our eyes, ears, and all these human elements, our organs, they are picking, or our senses, they are picking up the signals from surroundings, and our brain process it, right? Now, instead of our eyes and ears picking up signals, now the sensors are picking it up. Now, where is the brain? That's where your edge computing or the on-prem computing come and help. Now now you have replaced your sensors with sensors. You replace with your brain with computer, and what connects the sensors to the brain? That is your nervous system. And you know that nervous system, there is no latency. You touch something, you feel it immediately. And you, at least, I can't figure out a latency there. And that's exactly what the next generation connectivity infrastructure has to provide, close to zero latency. I'm bringing these points in to highlight how the application landscape is evolving and how the infrastructure around, have to evolve to cater to the next generation application. So keep in mind the huge number of sensors, the amount of data they generate, and the huge compute power required to replace that human brain, right? So just wanted to introduce that before we step into, I don't want to, into the 5G service type. I don't want to spend too much time on this 5G. I'm sure this is like a week-long conversation that you are listening to. And I'm sure that some people would have talked about 5G, different types of services and all. But I want to highlight few critical things that we all should keep in mind about 5G. 5G is not just about moving from 1G to another G, like we have done for 3G to 4G. It's not just a bandwidth upgrade. 5G is about three critical things. It's about bandwidth expansion for sure. It's about densification, and it's also about the deterministic or the low latency, right? That's why you have three service categories. One is ultra reliable low latency, that is primarily targeted for mission critical applications. Then you have fixed wireless access, where you need high speed internet access. EMBB is a good candidate for that. Then for the densification part, when you're dealing with millions of devices in a square kilometer kind of distance, you need massive machine type of connectivity out there to cater to that. By the way, if you have any questions, feel free to stop and ask those. And now let's look at, in order to segue into the need for edge computing, let's look at how the transport infrastructure evolution is happening. I'll use this. This is a typical slide that we use in Cisco to explain the transformation. Right, those of you who are familiar with the LTE network architecture, at a high level, what happens is you have a UE device. It's connected to, this picture is a bit of a hybrid with some level of disaggregation, but I'll try to explain it. So you have a UE, it is talking to a cell site where you have an antenna that is picking up the signals. And from the antenna, you have what you call it as a radio unit, which is attached very close to the antenna. You pull a coaxial cable from that and connect it to what we call it BBU. All of these are collocated at the cell site. So you have the RU, coaxial cable, and the BBU. This whole solution is what they call E node B in the traditional architecture, right? You can see this oval-shaped dotted line out there, right? You have RU and the BBU, and that whole concept is E node B. And in some cases, we call it, that's the RAN network, called Radio Access Network, right? Essentially, this BBU is doing heavy lifting of a lot of the DSP processing, where you take the information that are encoded into the radio signals and try to convert it into meaningful IP traffic, right? And from the BBU onwards, you connect to the rest of the network through something called a cell site router, carry the traffic through the backhaul network to the aggregation, and finally to the regional or the central data center. One thing to keep in mind is an integral part of any wireless network is what you call as a packet core. And in 4G, it is called evolved packet core. And in 5G network, is the general term used is NG core. right? So this is pretty simple design that you see in the top. Now, like I mentioned earlier, one of the major changes that was happening in the 5G is higher bandwidth, and second thing is the densification. So let's take one of them at a time. So in order to achieve very high bandwidth, you have to start operating at a very high frequency. So in the current frequencies that you use, which are below 6 gigahertz, with the LTE and all, you can get a decent, bandwidth, right? But to go well beyond that, and if you are looking at like, a broadband access kind of bandwidth for several subscribers, what you will end up in doing is having these smaller millimeter wave antennas, which are, using the very high frequency signals. And as you know, such signals can get interference or blocked by all the big towers and all buildings and all of that. So in order to achieve the kind of bandwidth and the density that you want, you start deploying what you call the small cell sites. Right, the typical cell site that you commonly see around us, these are called the macro cells. Right, so we need to have much smaller cell sites located everywhere. Like for example, you're going to an urban location like Delhi or Bangalore or Mumbai, right? You need to have several of these small cells to cater to the bandwidth and the density requirements of the subscribers there. And when you do that, these E-Node B devices are pretty expensive. And if you decide to have dedicated each E-Node B for each cell site, it's going to drive the capex up. So in order to build an efficient architecture, what is being proposed is the expensive resources. Let's disaggregate that and move to a central location and try to make use of that those resources very efficiently. So in a way, if you look at it, use sort of a multiplexing of the resources and use them when they need it, rather than statically preserving them even when they are not used. Right. So the whole concept of CRAN is around this disaggregation of the E-Node B device into multiple functional elements. Okay, I will talk about the functional split later, but for the time being, assume that you have a RU or an RRH device at the cell site, which is called the radio unit, right? Now, over a ORAN compliant or eCPRI or the CPRI kind of interface, you can connect it to your packet network, right? The first place is called the Fronthaul network. Then from the Fronthaul networks, you can have a smaller compute element sitting there, which is hosting this baseband processing, right? This is mostly related to the radio side processing, the DSP processing that I was talking about. And you can also opt to have what you call more like, a centralized processing, which is like in typical case, a PDCP kind of layer, right? That is at the packet level at a even central location to pool the resources. Or you can choose to have both DU and the CU together if you have some latency requirements. I'll talk about those later. But what I'm trying to highlight here is this E-Node B device that you see in the upper part of the picture, it got disaggregated into three pieces. One is RU, another one is the DU, and third one is CU. Depending on the service requirements and what level of pooling that you want to do with these resources, you can go and you have the flexibility to go and place them at different locations in the network, right? And they are hosted on the computing elements, right? So I'm just trying to introduce the concept of why compute is required at different places in the network. Even if application doesn't require it, our next generation networks may require these compute elements to host what we call the virtual network functions. Moving on, I just wanted to capture very high level view of that radio processing stack. Without getting into the details, if I have to stack it from the RF layer onwards, there is a PHY layer, which is the physical layer processing of the radio. And then there is MAC level. This is where, most of the scheduling and things will happen. Above that is the RLC layer. This is radio link control protocol. In a way, I would think of this as like a TCP for the radio layer. And this is the layer where there is a lot of segmentation, reassembly, concatenation of the packets happen. And there is a good, sliding window mechanism here to make sure that there is a guaranteed delivery of the frames between the baseband unit and the endpoint or the UE, right? So this layer take care of all the retransmission and everything. And the PDCP is the packet data context protocol, and that actually gives you some of the functionalities like, again, interface with the application plus sequence numbering, ciphering, and all of that is provided by the PDCP, right? And when we talk about, RU, DU, and the CU, typically people try to split it at like, the option level that I'm showing it here, and everything from this layer, that is the hi-fi, all the way to the high RLC, try to do it in the DU, and the CU kind of wrap the functionalities of the PDCP and some other functionalities, right? This is how a typical split is done, but depending on your operator and the network choices, there can be multiple options. Again, that is not very relevant for the edge computing discussion. These are some of the standards which I don't want to go through. So now we talked about the split. We talked about RU, DU, CU, and what are some of the functional placement options for these elements in the network, right? So you can have like, the cell site hosting the RU, having both DU and the CU functionalities, which essentially mean that every edge site that you're having, you need to have compute and the acceleration elements to host these functionalities, right? Another model is where you can bring in the DU functionality as well into the cell site and have the CP, the control plane for central functions, CU functions into the edge site. The advantage is it kind of reduces the bandwidth that we need to reserve if we are going through a third-party network, right? And I don't want to go into each one of these models, but what I'm trying to say here is there is no hard and fast rule on how you place these functional entities. It all depends on the end user requirement, applications, and all of that. And single deployment itself can have multiple flavors of this deployment. And all our edge computing strategy should be done to align to support all of these models. Moving on, this gives you more like a bird's eye view of how these sites are kind of aligned, right? We have this concept like, access site, edge site, pre-aggregation site, aggregation site, and all of that. And what I'm trying to convey here is as we move away from the user or the cell site, the number of locations where you place the compute, that reduces. But the cons with the approach is like, as you move away, the round trip latency to go to the next compute and come back is going to go up, right? So there is an impact to the overall end-to-end latency depending on where you place the edge computing entities, right? So again, it's a design choice we have to make. These are the options that are available to us. That's what I'm trying to highlight here. This is another view of the previous functional placement. This just with some realistic numbers pulled from the field, but it can vary depending on which customer, how big of a backhaul network it is, and all of that, right? So this model shows, you have everything placed on site, including your UPF. Okay, by the way, UPF is the user plane functionality, which essentially is a first entity that look at the traffic that is coming from the end user and forward it to the data network, right? So that's a user plane functionality, which they take care of the forwarding. So in a real conservative model where you want to bring in all the processing, including your RU, CU, DU, and the UPF, all of that into one location, it helps us to achieve the super ultra, fast, processing. Right? This is true ultra reliable latency mechanism. Everything at the cell site. Think of it, in the original architecture, we had only the E node B devices at the cell site. Now, in this model, you're bringing in the UPF, which was sitting in the core network, into the cell site. And you're also bringing in a small MEC kind of compute element there, which is going to host the application. So if you have a gaming applications which requires like super fast response, this may be a choice. It can guarantee you the latency. But there are hundreds of thousands of such cell site locations. You try to bring in compute to all of these places, it's going to put a lot of stress on the overall network architecture in terms of cost, operational overhead, and all of that. So it's a model, but is it a truly deployable a model in the mass scale network? It's questionable. Other option is you having the RU at the cell site, DU at one of the tier 1 location, so that you can meet some of the infrastructure specific latency requirement. I'll talk about that a little later, what that means. And then the CU, which is not so time sensitive, into a tier 2 site and collocate along with it. Right? So again, these are different models. And as you can see, this model, you have a millisecond latency, but splitting it to tier 1 and tier 2 locations, you are talking about 10 millisecond or more. So you have to find the ideal deployment, based on your deployment scenario, you have to decide on the ideal placement to cater to your end user needs. Let me get into the core of the topic. With all this introduction, all I was trying to do was trying to bring in how network is getting disaggregated. Why do we need to disaggregate the network? It's not just a transformation for fun. It's more like a transformation driven by application requirement, and more like providing a seamless experience to the end user, right? They don't have to deal with any of the infrastructure complexities. That's where disaggregation really helps. It helps with flexibility, scalability, and all sort of monitoring. And like we discussed, decomposing the RAN, placing one element in the edge, another one in the aggregation space, and all those flexibilities are the outcome of the disaggregation. So it's driven by the next generation applications. It's not a normal network transformation, is what I'm trying to say here. So in all our application discussion, there were two key elements I was trying to bring in. One was the huge sheer volume of data that is generated by millions of users. Actually, to give you a rough idea on the the volume of data that are generated, what I read in one of the Tesla white papers is, a car which is like, they call it layer 3 thing, that is a semi-automated car that can potentially generate 25 gigabytes worth of data per hour. 25 gigabytes per data. Think of an Uber driver driving a Tesla. It's a little unrealistic scenario, but just think of it, driving a Tesla 12 hours a day. 300 gigabytes of data per day is generated by an automated car. It sounds unbelievable. Actually, back in 2015, my data limit at home was like 50 GB per month, and now we are talking, and now I have unlimited, but still my consumption stays within 100 GB, even with everybody working and taking school, attending the online classes. It's still within 100 GB, and now we are talking about 300 GB one car generating per day. I'm taking 12 hours of ride. It can be, we can always argue that 2 hours is the average drive time and say it's 50 GB, but still it's huge amount of data and that needs to be processed. If you decide to send all this data all the way to the cloud, we are just going to run into bottlenecks everywhere. If you have 100 cars in a vicinity and everyone generate this data and push it to the cloud, you're talking about what, 30 terabytes of data from those 100 cars per day? It just has impacts on the overall network bandwidth. It's going to create a lot of choke points. It is going to stress your whole cloud system. You need huge database to store this information, right? So reducing the amount of data that goes to the cloud or to the backhaul network is very, very critical from a cost perspective, right? Every bit that we generate, if it lives in this planet for additional millisecond, it is going to have an environmental impact. Right? This bit has to travel. To push this bit out, I'm sure you have to use some electricity. You need to have fans to cool down all the devices. So overall environmental penalty for keeping a bit alive in the universe is also, it's something we should watch out for. So data reduction is very, very key. Second aspect that I talked in the context of the application was deterministic latency. When we move from one place to another place in an assembly lane, there has to be coordination. Think of your assembly lane where we are packing the biscuits, right? We took a box. The first robot pushed a box into a conveyor belt. The next robot needs to put 10 biscuits into that box. Third one needs to just put a wrapper and seal it. If these things don't happen in a coordinated fashion, all the biscuits will be on the conveyor belt, not on the box. So the moment the box is placed, there has to be a coordination to the next element who need to place the biscuits into the box. I'm just picking an example to highlight why these things, latency, deterministic latency is very, very important, right? So that tight coordination and deterministic latency, that's the other aspect or the attribute of the next generation application, right? Or the requirement. So these two are the key drivers for the multi-access edge computing requirement in the future networks, right? Primarily the data reduction and the latency reduction. Now, a third aspect of the edge offload I will bring in. So I'm sure most of you play some sort of online games. Those who have played games during the ancient days, like 10 years ago, you know how costly was PlayStation consoles that you had at home. There's a bigger device, very expensive, and all the logic and everything, GPU and everything that needs to be processed was packaged into that box. Now with online gaming, there is an opportunity to keep the console at home dumb and lightweight, less costly. If you do that, somebody has to heavy lift the processing, right? So all the video rendering and everything that has to happen as part of a end-to-end gaming application, someone need to really take over that. We can always say that we go to the cloud, get everything done there, and video rendering happen there, and final image will come back to the console. And as always, cloud, depending on where in the world you are and which is your nearest cloud, it can take 100 to 200 millisecond or even more. So this can have an impact on your gaming user experience, which essentially means that placing a GPU kind of device which take care of the gaming processing at the edge location will help us to offload some of the functionalities, offload some of the brain from the console to the edge. That's the third class of applications that will be driving the edge computing, in the future networks. Any questions so far, folks? I hope you are able to hear me, and so far all good. Hey, Professor Rajput, can you hear me? Hey, Professor Rajput, can you hear me?
Sir, I guess we can hear you.
Okay, sure. Okay, I was worried that my audio is not clear. So just checking. I will go back to sharing mode. I hope you can see my slides back.
Yes, sir.
Okay, good. Thank you. So I'm going to skip over this slide. In my conversation so far, I tried to highlight this. This is again talking about how the latency get impacted as we move towards the core network, right? The cost of the backhaul is going to go up because you are carrying a lot more bandwidth, and the latency is much going to go up, incrementally, right? At the same time, if you try to bring in the cloud all the way to the cell side, knowing that there are hundreds of thousands of cell sites, the operational complexity is going to go up significantly, right? Managing hundreds of thousands of locations is not an easy task. So we have to strike a balance between these two to achieve an optimal deployment scenario. Again, one last concept I wanted to bring in this context of the edge computing is the slicing, right? This is about carving the resources. So like I said earlier, 5G is about bandwidth, deterministic latency, and the user experience. And if, for example, an IoT vendor, like say, for example, Delphi, wanted to get a deterministic service for all their IoT services because they ship a lot of things to their end users. They want to monitor those sensors using an application sitting in the cloud. And if they wanted to carve out the transport resources, you can create, say, for example, a URLC slice, which actually do a slicing of the transport network, and then also do some level of reservation of the compute element to give a deterministic user experience. This is more important from a network and the resource perspective, not from the MEC perspective. I'm going to skip over the slicing and just get into MEC reality picture, right? So all of that we talked about was basically I was trying to convince or tell you that why we need this multi-access edge computing, right? And to summarize our discussion so far, there is a massive network transformation happening to improve the efficiency of the network and also to support the next generation applications, right? And this transformation is going to disaggregate a lot of the monolithic entities that we have seen in the past network. And as we disaggregate, a lot of these functions are going to get virtualized. And in order to host these virtualized network functions, you naturally need a compute elements built throughout the telco or the SP networks, right? So that's the conclusion we had so far. Now let's take a stab at, what exactly is happening in the real world, I'm going to give some of the results of some of the experiments that I've done. So just to give you a blueprint of a very, very high level end-to-end network, right? So you can see on the left side, these are your user equipments, UEs. Then you have your radio cell site with your G node B. Through the backhaul, you're connected to the packet core network, right? Sitting in your regional data center or the central data center. Then you have the ISP backbone. Through the internet, you are getting into the hyperscalers backbone and then to the cloud, right? I'm just picking AWS as an example for the cloud, but any hyperscaler, this is the story, right? So any application that is running on these end users equipments wanted to access a cloud application, it just goes through this all segments in the network before it get to the cloud, right? I'm not going to get into details of EC2, DynamoDB. These are some of the services offered by AWS. I just captured it for reference, right? But just you need some of these to run your server applications, right? So now what exactly are we talking about? What is this picture, what it means to edge computing, right? So I'll take an example. AWS has a service called Wavelength. In a way, it is an extension of the AWS cloud with minimal services, right? AWS cloud has around 130 services today. But Wavelength is a mini such instance. It supports 5 or 6 different services, not all, right? The minimal required services is what it supports. So what the experiment that I'm talking about is they brought in this AWS Wavelength concept and worked with Verizon to install this Wavelength into Verizon's edge locations, right? To understand the benefit and the real world picture of doing this. And Verizon made it as like a 5G edge service. They made an offering for all the application developers to come and develop application which works in a hybrid manner at cloud and the edge locations. And then they launched this service to 10 different locations. Why I'm bringing this thing is like, to tell you the reality, what is happening in the real world, right? How they did this? So basically what they did is they built a data center in a box. Like the multi-access edge computing platform that comes up in all the conversation, they took a box, they call it Outpost. They shipped it to Verizon. Verizon connected it to one of their routers, kept it in one of their edge locations, right? That's where they hosted the Wavelength, which helped the users to launch some of the services at the edge to understand the application level benefits. In a nutshell, if you look at what they did, by shipping this hardware, they basically extended what you call as the virtual private cloud, which you typically create in AWS, and it sit in the cloud. They extended it to the edge location, right? They brought some of these EC2. EC2 is a AWS Elastic Compute Cloud, right? So EC2 and some of the services, they brought it into the edge location. With this, what will happen? Now, anybody who is familiar with AWS tools and who is familiar with AWS API and the application infrastructure can just build an application seamlessly and host it at the edge. And that application can consume the data way early on before it go to the cloud. Now, the current benefit of this model, what they gained, and all of that is still in analysis state. Experiment is continuing. There are a lot of questions about, what is the monetary benefit or the revenue implication of doing this? Today, there are no convincing applications, which they can put in there and, generate money from the end user. but that will evolve eventually. But this is the ground reality of what is happening in some of the edge computing experiments in the real world. So now putting the previous slide along with all the functional virtualization, network function virtualization that we talk about, once you bring in the cloud, power of the cloud to the edge, some of these telco VNFs that we talked about in our original disaggregation discussion can go in there, right? Whether that is the right place or whether they should stay within the telco, that's again a debatable point, right? But there is a potential to move these networking functions into the edge as well. And also potentially, if you try to superimpose the cloud edge model and the networking function, networking disaggregation, you probably think of like, a telco infrastructure where you have the whole MEC infrastructure running in the telco network, and you have a software abstraction over which NFV software abstraction over which you run all the VNFs. Then another piece of this infrastructure can have the MEC compatible APIs and functions where you can bring in the functions from the cloud providers, so that we have both the application infrastructure and the network function virtualization infrastructure collocated at a MEC location in telco network. Right, so this is potentially one way of doing it, right? Bringing in the cloud to the edge, taking the telco network functionalities also to the edge, and creating a win-win situation is what I'm talking about here. So this is the ground reality. And now what is happening? So okay, when you do this, what are the benefits that are going to come out, right? From a telco perspective, they have the full control of the edge location ownership. They are, the connectivity provider, and they offer infrastructure as a service to the cloud providers. So if you have the ability to bring in the cloud to any POP location, right, like we discussed in the context of the wavelength, it actually reduces the gap between a telco infrastructure and a cloud infrastructure, right? So what are the other value adds that can be brought into the overall edge computing concept in the context of telco, right? So this is where your radio network information services, your UE location information, all of these are information that are very, very relevant to telcos, and they have complete control and visibility of this information. So you take this information and try to make application more intelligent. For example, say you're doing a video caching at this edge location. Now, your radio network information tells that the signal quality to a particular user equipment is pretty bad. Maybe this video caching solution can use that information and say that, oh, this user bandwidth experience is pretty bad. I'm going to take a video file which is like a encoding type with which requires very low bandwidth, right? So that the end user get a seamless experience, right? These are the kind of evolution that can happen in the application space by tapping into the the information that telco can provide, right? So that's where a marriage between the cloud and the telco that happens at the edge location, that is very, very powerful, right? And with this in mind, we know that there is a lot of experiments happening in the field. There are a lot of people doing trials. There are a limited set of real world deployments. If you look at future, what are the applications that is there in foreseeable future, that may make benefit from the edge computing at a telco location, right? So one common one which we see, I'm sure this is probably happening in Varanasi as well, the smart city initiative, right? This is happening across the board, right? Everywhere in the world. And there are certain smart city applications, not everything, not all smart city application may require edge, but there are applications like, the surveillance cameras that is there on roads, traffic signals, and all of that. Those generate huge amount of data, right? So that is one space, probably a segment in the smart city concept where telco edge can help, right? You look at Industry 4.0 or the factory automation. This is where I believe having a mobile edge computing at the telco premises may not be very valuable in the short term. In these cases, an on-prem compute infrastructure or the edge compute infrastructure is preferred. The reason being, you don't want to go through the entire network to reach that edge computing location when you are dealing with critical services, right? There is always a latency impact there. CDN is another area. It's a debatable point, right? It's kind of neutral. Gaming is something that we talked about. Definitely, we can, from a cost perspective, telco edge can bring in benefit. Network infrastructure is another important aspect where you have a lot of different network functions that are getting virtualized, and host these virtualized network functions in a timely fashion. Edge computing may help, right? And home surveillance is another area, right? So if you look at all of these applications, the common theme that you're going to see is video processing, compute offload, and the image processing, right? These are what we applications, end user application acceleration that we can see in foreseeable future. As we do more experiments, I'm sure more and more use cases are going to evolve, and we will see a lot more, need for different accelerators at the edge location. All of this is good, but until none of this makes sense until we have a good deployment plan on how to get these edge computing infrastructure to the real world, right? So right now, like in any other new technology, even the concept of the multi-access edge computing, there are a lot of deployment barriers. The first one, in my view, is the major re-architecture that we have to go through, right? This is not a simple transformation. This is a major re-architecture. We are taking a lot of monolithic entities and then decomposing them and, orchestrating them on a need basis. There's a lot of risk involved, a lot of operational complexities involved, and I'm sure we will get there. But that is one of the key barriers there. Second thing is, I would like to highlight is the application impact itself. See, some of the applications that are deployed in the cloud, they will seamlessly work in the edge if depending on the type of the application, right? You just create another virtual machine or a container out there in the edge location with that application image, it may just start working, right? Maybe as simple as that. But some of the applications may require some re-architecture. You may have to go through some sort of hub and spoke architecture. I'm not saying that it's true everywhere, but potentially this can impact application migration or slow down the application migration. Another key element we have to keep in mind is the huge cost involved. This huge upfront investment to bring in all these infrastructure elements to the network, right? So every time when I spend $1, I will think, can I get $2 back with that, right? So that's how investment work. So when telco or service providers try to invest in MEC, the first question is like, how do I monetize? Can I get a 20% premium from my subscriber if I offer him like, a 40% improvement in the latency? Answer to that question is not very clear, right? So these are the barriers that are holding the mass scale deployment of the edge edge computing solutions, right? I'll just, highlight one thing that is happening in the industry. There is a forum called HC-MEC. It's driven by several industry bodies, including several service providers, equipment vendors, operating system players, cloud players. Everybody is part of this. Where they're defining an architecture for MEC, right? Where, which talk about how you virtualize the resources, right? Using the virtual infrastructure managers. How do you take these virtualized resources and create different function, supplement the functionalities required for the MEC, right? For example, we talk about the RNIS, the Radio Network Information Service, and all of that. See, these are the functionalities that are specific to MEC. How do we create a generic interface between the physical infrastructure and some of the software infrastructure like the MEC platform infrastructure, which provide a lot of MEC specific services to the application, right? So there are standard interfaces the industry forum is defining so that anybody can build a MEC platform and drop into a physical infrastructure. And any application vendor can get a third-party physical infrastructure MEC platform from another provider and put an application on top of it, right? So all these combinations should be possible for a mass scale deployment. Otherwise, if we go with a monolithic model, it is going to prevent the accelerated deployment of the multi-access edge computing. So this is an industry forum that is driving the standardization of the overall MEC concept. And there are products slowly becoming available, and you will see more and more of such products coming out as well, right? And if you ask me, how do I define a MEC host platform? This has to have all sort of resources that are required for the next generation application. And it can be your compute element, it can be your storage, it can be your networking like you have today. It can be a cluster of GPUs, FPGAs, and any other resource you name it, right, which are not available today. Could be an AI engine, many such things, right? So essentially, whatever processing and activities that were happening in the cloud that are actually getting replicated in a smaller way at the edge with limited set of functionalities to create more end user value, right? That's what MEC is all about. And the standardization effort that we talked on the slide is all about accelerating those deployment by creating a truly interoperable sub-components in the MEC infrastructure. That's pretty much I have on the technology and the why part of the question that I have raised at the beginning of this conversation. And what next should happen? This is more like, thought for all of us, what we should be looking at, right? The key part is, one is the first thing that has to happen is the network infrastructure virtualization. That has happened to a good extent, continuing to happen, and I'm sure more and more will happen in the future as well. Second thing, identifying the application, analyzing the application that is monetizable, right? It doesn't make sense to take any application and move it to the edge if there is no additional value we are going to create out of it, right? If I have to compare a cloud and a MEC is going to be definitely more expensive from a processing standpoint because it's a much smaller entity, right? And the real estate, power, and all of that is a premium at the edge locations. And if you don't see a compelling reason to put an application in that expensive location, don't put it. You won't be able to monetize, right? So to take advantage of that user experience, you have to really, really identify which application makes sense at the edge locations, right? Again, I talked about the common theme earlier, but at least I personally feel gaming, edge inferencing are probably some of the breakthrough areas where probably the industry is going to hit fast, or maybe there are other applications that also will evolve, right? And second aspect is creating the edge infrastructure, right? At the end of the day, the operator goal is to have a lower capex, opex hardware, the really standard complex software infrastructure, and cloud style developer experience, right? These three are very, very key for the successful deployment of the multi-access edge computing, right? So with that thought, I would like to close this conversation. And if you have any further questions, do let me know. All right, if there are no other questions, I hope it was a useful session. And if you have any questions, feel free to reach out to me over the email, or if you want to zoom into any other specific topic in future in this domain, please let me know that as well. The idea today was like, just to get an answer to the why part of the question, why we need the edge computing. If you need to go back a little bit more deeper on the design aspects or other areas, definitely we can have another conversation. So Professor Rajput, if there are no further questions, I will probably close this conversation. Is that okay?
Hello, sir. He has gone out for a while. I will inform him.
Yeah, sure. Thank you. Thank you so much. And you all have a great weekend. Enjoy your day.